Okay, now we're going to start talking about automata. Specifically, we're talking about deterministic finite automata, or DFAs. So what's a DFA? Informally, a DFA is like a little machine that takes in strings and reads the strings one character at a time, transitioning from state to state until the entire string is consumed. And the DFA will either accept or reject the string if you end up in a final state or not. So here's a formal definition. A DFA is a 5-tuple, so a tuple of 5 things: sigma, S, S naught, F, and N. Sigma is the alphabet, and the alphabet of the DFA is the set of all characters you can make strings from. Usually we're concerned with either the set of all binary strings, 0, 1, or sometimes a set of a few letters, A, B, C, etc. The alphabet for DFAs is always a finite set, so usually it's going to be binary strings. Capital S is a set of states. The finite and deterministic finite automata tells us that there's always finitely many states, so there can't be infinitely many states. Finitely many. Okay? S naught, which is an element of S, is the initial state. And the initial state is the state that you start from when you start reading a string. Initial state is always denoted with an arrow. Denoted with an arrow. Pointing into a state. So as you can see here in this diagram, S3 is the initial state. F, which is a subset of S, is the set of all final states. There could be more than one. So the final states are the states that if the DFA reads a string, and when it's finished reading the string, it halts in one of the final states, that means the DFA is going to accept that string. Final states are denoted by a double circle. So for this DFA here, there's only one final state, S5. There's no reason why there couldn't be more than one final state, but this particular DFA has only got the one. And the tricky one is N. N is a transition function. It takes a state, and it takes a character, and it tells you where to go under that state. So I've got a little example here. If the transition function says, if the current state is S0, and if I read A, I transition to S1, graphically that's represented as the state S0, the state S1, a little arrow saying, if you read an A, move from here to there. So in this diagram here, we could say, if I'm in S3, and I read a 0, I transition to S4. Okay? And that's the definition of a DFA. And because this notation is quite clunky, we usually represent DFAs as little flowchart diagrams like this. So if we wanted to take this DFA and write it out formally, or we could write it out, so let's call this DFA or call him D. This DFA D is equal to a 5-tuple, sigma S, S naught, F, N, where sigma, so sigma is a set of all characters that this DFA operates on, in this case only 0s and 1s. S is a set of all states, S3, S4, S5. S naught, which is the initial state, in this case is just S3. There's always only one initial state. If there were more than one initial state, you wouldn't know where to start from. F is the set of all final states, so the set containing S5, not just S5, but the set containing, because again, there could be more than one. And N, which is the transition function. The nicest way to write the transition function is to write it out as a table. So you have each state here on a row, and each character here is a column, and then you just enumerate all the combinations. So if I'm in S3 and I see a 0, I go to S4. If I'm in S3 and I see a 1, I go to S5. And you get the idea. So S4 under a 1 goes to S3. S4 under a 0 goes to S5. And once you're in S5, reading a 0 or a 1 will take you back to S5. States like this, where once you're in them you can never leave them, we usually call them trap states. So we can say S5 is a trap state. i.e., it traps strings that get to it. So that's the formal definition of a DFA.